We've now got some pretty good intuition for iterative least squares. We have that quadratic surface, those contours, and what we want to do is, starting at some random point in there, we want to make our way iteratively, of course, down to the minimum. And the way we're going to do that is we're going to pick a direction. How? Don't know yet. But what we know is that it's going to be the steepest part of that contour. We're going to take some step until that error starts to increase. And then we're going to repeat, 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 eventually making our way down to, iteratively, down to the minimum. Now, in order to determine the direction and the step size, I need to introduce the quadratic form, what is termed the quadratic form, which is simply taking our quadratic error function and just writing it in a slightly different way. So let me just go ahead and do that, and then we'll figure out how to determine the iterative direction and step size for this minimization. So this is the familiar quadratic error function, E of u. U, of course, is slope and intercept in this line fitting example, or it's the a, b, and c terms for the fitting of a parabola, is equal to the vector norm of xu minus y. Remember what this is. Xu minus y is a vector. This vector norm squared is the same as taking the transpose of the vector times itself. So let's go ahead and write that out. So xu minus y transpose is here times xu minus y. Good. Remember that when I have the product of two things and I'm taking the transpose, that's the same as transpose and reverse them. So xu transpose, quantity transpose is equal to u transpose, x transpose minus y transpose times xu minus y. Good. So that's my quadratic form just written out. Let's go ahead and do the cross multiplication here. So I've got a u transpose, x transpose u, that's the first term here, times the first term here. I've got two of these intermediate terms, y transpose xu and u transpose x transpose y. By the way, I can play with the transpose to get those to look the same by just transposing the whole thing and flipping everything and transposing the individual pieces. So that gives me minus y transpose xu minus y transpose xu. And then, of course, I've got plus y transpose times y. Notice, by the way, that this is a paraboloid. I've got a u squared term here, a u term here, and a constant term here. That's exactly what I expect, given that I've got a quadratic error function. Let me bundle up some of these terms and do some variable substitutions to simplify this equation. Let me go ahead and call x transpose x the matrix A. So A is just x transpose x. Let me call a y transpose x B transpose. Notice the transpose there. I've done that because later on I'm going to transpose that vector and I want to lug around a B instead of a B transpose. So B transpose is y transpose x times u, that's that thing right there. There's the 2 because I have the two terms, plus some constant c, which is just y transpose y. This is the so-called quadratic form. Notice that it's quadratic because I have a square term here, I have a linear term here, and I have a constant term here. And all I've done here is just simplify the notation so I have an A matrix, a B vector, and a constant C. Remember, A matrix, B vector, and C scalar are derived from our data. Yeah? A depends on the X matrix, B depends on the X matrix, and C, of course, depends on that Y vector that we derived when we were doing least squares and weighted least squares. So this is my quadratic form that I need. Now, what is the intuition for doing iterative least squares? The intuition is that we want to move in the opposite direction of the gradient. The gradient tells me where it is steepest, and I want to move in the opposite direction. Well, how do I figure out the direction at any point in this paraboloid? I take derivatives. That is, after all, how we found the minimum. We set the derivatives equal to 0. Now I'm up somewhere here on the paraboloid, up in the middle, on the top here, and I want to know what is the steepest descent. And so the way to do that, of course, is to take derivatives at that point and then move in the direction. So let's take the derivatives here. I could have taken derivatives here, but you'll see in a minute that when you take derivatives of this quadratic form, which is simply a rewritten version of the original quadratic equation, things are going to get a little nicer for us. So let's go ahead and take the derivatives. Well, let me start by taking the derivative up top here. The derivative of xu minus y squared is, of course, just equal to what? It's equal to 2x transpose x minus u. We've seen that now over and over again. So I'm just taking the derivative of that quadratic error function. Let's actually write this out now and see what happens. So what is this? Let's see. Let me multiply through. So I've got the 2x transpose xu times, minus rather, 2x transpose y. So I'm just multiplying that 2x transpose into here. And so this is my derivative. And let me simplify a little bit more. What is x transpose x? It's equal to a in my quadratic form. So I can substitute that in right there. And what is, let's see, x transpose rather, y? Well, that looks an awful lot like this transpose. So if I take the transpose of b, then I've got x transpose y. That's why I did the transpose here. So this thing is just minus 2b. I'm not going to care about that scale factor because eventually I care about direction and not magnitude. So I'm going to go ahead and drop the 2 out. And the derivative is au minus b, where a is x transpose x and b is, well, b transpose is y transpose x, so b is x transpose y. So there is my gradient now. And why do I want that gradient? Because that's the direction I'm going to be moving into. Actually, I'm going to be moving in the opposite direction of that because that tells me where things are the steepest. Okay, so all of that, that quadratic form and then that differentiation was to write the gradient in terms of the x matrices, the x transpose x, and in terms of the x and the y. And now we know for any point on this contour, I now know the steepest ascent and the steepest descent, which is just in the opposite direction in the negative. So now I have some intuition for direction. I still haven't quite nailed it yet. We're going to get it in a minute, but there's still that question of step size. So when we come back, we're going to formulate the two things we need to do this iterative least squares. What is the direction you need to move into based on the derivative, and then how much, which is going to turn out to be a little bit trickier, but we'll get there in a minute.